Hi everybody. We're definitely here at Unit 6, the first lesson, the third video to finish so we can have these kind of in little chunks. And so chunk number 3 is doing implicit differentiation and doing a tangent line problem. Okay, so implicit differentiation. Implicit differentiation doesn't change, okay, how it works. So we're using it in concert with taking the derivative of a natural log or any other function. And remember, if we're using implicit to find dy dx, that would mean x is the normal variable in the derivative process, where the y is the term that will create an implicit. And I think we're going to do number 18, and then I think we're going to do number 19. They're all kind of fun. I know you guys are like, yeah, you're sick. Okay. So here I am taking the derivative implicitly. Number 18. Derivative of 4x squared implicitly is 8x. Derivative of 2 natural log of y would be 2, 1 over y. But we're taking the derivative implicitly with respect to x, so I'd have dy dx. Plus the derivative of y cubed, 3y squared, dy dx equals 0, because the derivative of 12 is 0. Now, if you were with me, I would say, okay, what do we do now? And hopefully you would be like, I gotta get, oh, we have an announcement. Or maybe that's the warning bell. That's fun. Okay, I'd say, what are we going to do now? And you'd say, well, we're going to get the dy dx's all on one side, and everybody else goes to the other side. So in this case, the only other guy is 8x. So how about 2 over y dy dx plus 3y squared dy dx equals negative 8x. And since I've got an unlimited amount of space here, I'll just barge into another problem. So ultimately, my expression for dy dx is going to equal negative 8x over 2 over y plus 3y squared. Now, that's not the prettiest expression, but if I multiply everything by a y, that will eliminate the fact that I've got a fraction inside of a fraction, and that will give me negative 8xy, and that will give me 2 plus 3y cubed. That's a very pretty implicit derivative. If I wanted to talk about horizontal tangent lines, I would have to be thinking, okay, well, how would that derivative that I just wrote equal 0, which would mean I'd have to think about the numerator equaling 0. If I was going to think about vertical tangent lines, I would have to think about this derivative being undefined, which I'd have to think about the denominator being undefined. Now, here's what I like about number 19. My screen capture toolbar to grab number 19. Oh, that's the bell. I am in school making you a video. All right. Okay. Number 19 is going to be a lot easier if I rewrite the natural log of xy. If I rewrite that as the natural log of x plus the natural log of y minus 3x equals 4. Okay, I'm going to make a little note here. Rewrite LP, log properties. Rewriting that using log properties gives me two things to take the derivative of that are pretty easy. Derivative of natural log of x is 1 over x. Derivative of natural log of y is 1 over y. Implicit to x means have the dy dx minus 3x equals, don't forget, derivative of constant is 0. 1 over y times dy dx will equal 3x minus 1 over x. So how about multiply by y, and dy dx will equal 3xy minus y over x. That's kind of a fun derivative. Now, why I chose this one to do, a couple reasons, is I want to show you how if I don't rewrite this, it'll still work. I can still get the derivative, and I'll actually get the same derivative, but it might be a little uglier. So, I take the derivative of the natural log of, that's u, xy is u. I would have to have 1 over u times the derivative of u. So the derivative of xy would require a product rule, y times 1, x times dy dx, minus 3 equals 0. Did I get did I take the derivative of that? I didn't. Why didn't you tell me? You're like, I was yelling it. I was yelling it at the video, and you weren't listening. You're right, because I didn't take the, you know why? Because I didn't take the derivative of 3x. I just wrote 3x. So here was I taking the derivative, 3x becomes 3. Okay. So it's 3 minus 1 over x on it. So how about, that's even. Well, I'd have been really confused when what am I doing? I'm doing crazy stuff. I would have been really confused when I didn't get the same answer. Okay, so 3y minus y over x. All right. I did that on purpose. Okay, so now look at this nonsense. I gotta get this by itself. I probably would multiply by, well, I'll move that over and I'll multiply by that. So how about y plus x dy dx equals 3 times xy. So if I add 3 and then multiply by xy. And so I'd have x dy dx equals 3xy minus y. So dy dx would be 3xy minus y over x, which is 3, no, shame on you, Mrs. Willenbrock. Oh my goodness. 3xy minus y over x. I can split that. And then I can take that factor out. So how about 3y minus y over x? Yeah? Oh yeah. Do the happy dance. Okay, so, you know, we could debate whether what I did the second time was harder than what I did the first time, right? Harder is relative to how you understand things. So once again, taking the derivative of the natural log of a product, 1 over the product times the derivative of the product with product rule, okay. Rewriting the product as a sum and then taking the derivative of 2 separate natural logs, okay. I mean, I still made a mistake over here, so it's not like it's not possible to make a mistake, but just 2 different options for the same problem. Now, last thing for us in video world, I'm going to take ourselves out of dual page. If you haven't quite figured out yet that that's not going away, equation of a tangent line, I don't know where you've been, because every time you're like, we're doing a new lesson, like, oh, there's equation of the tangent line. Okay. In both of these cases, in both of these cases, I messed up. In both of these cases, I think I accidentally deleted the page. There we go, yeah. So in both of these cases, we're given the point. Tangent line equations in point slope form. So y minus y1 equals m times x minus x1. And we're going to get m from the derivative. And that derivative has to be evaluated at the xy. I've seen just a few of you kind of find the derivative and then write the derivative expression right here. This isn't going to be the expression for the derivative. It's the value of the derivative. It's the derivative and then evaluated at the xy. So, you know, really there's nothing super difficult about this other than everybody freaks out when you see an e. E is just a like that is just a number. E to the x is a function, but e is like a 5 or a 7. So the natural log, I mean, you can rewrite this if you want, but you know, saying the natural log of x over e is like saying the natural log of 1 over e times x, where that's a constant. I'm actually going to, we're almost at the 12-minute mark, so I'm going to leave these for you to try. You should be able to do a tangent line problem now, okay? Find the derivative, evaluate the derivative at the point, that gets your slope, write it in point slope form, and you get your tangent line. Okay, have fun with the natural logs.